Annenberg Media.
What a classic flick. You know, you can never tell where inspiration will strike. While I was watching Ben-Hur here, I was struck by an analogy between the Roman Empire and an important mathematical concept. Here, I'll show you. The Roman Empire began around the year 390 BC. And it lasted for centuries until it came apart at the seams around 476 AD. Now, how would you figure out the lifespan of the empire? Well, first of all, it doesn't matter whether the years are BC or AD. Years are years, after all. So we can just add the BC years to the AD years to get our answer, which is 866. 866 is the total number of years that the empire lasted. It's also the distance from this point to this point on the timeline that I've drawn. Now, here's the analogy. A timeline divided into BC and AD is just like a number line which is divided into positive and negative numbers. And the lifespan of the Roman Empire is similar to a distance on the number line that straddles zero. In the case of the timeline, we can forget about BC and AD and just talk in terms of years. We can do the same thing on the number line as well. We can forget about numbers as positive and negative and talk instead about absolute distance on the line. This idea of absolute distance is important in algebra, and it's one we're going to explore in this program. We'll see that the concept of absolute distance on a number line is called absolute value. We'll see how to solve equations that involve absolute value. And we'll also learn to solve inequalities involving absolute value. Finally, we'll pause for a look back at how far we've come in the series. Just as there are times when we want to know the absolute time between two dates, there are times in algebra when we want to know the absolute distance between two numbers. To deal with these situations, the concept of absolute value was invented hundreds of years ago. The absolute value of a number is the distance between that number and zero on the number line. Now, distance is always positive. We never think in terms of negative distance. So this distance on the number line is stated in absolute terms. For example, the distance of the number 4 from 0 is 4, but the distance of negative 4 from 0 is also 4. So the absolute value of negative 4 is 4. We indicate absolute value with this symbol. This means find the absolute value of whatever is inside. So the absolute value of 4 is equal to 4. And the absolute value of negative 4 is also equal to 4. The absolute value of negative 1/2 equals 1/2, and so on. Now, the absolute value bars only pertain to whatever is inside the bars. If there's a negative sign or any other numbers outside the bars, you find the absolute value of the quantity inside the bars first and then perform any additional operations. For instance, negative the absolute value of 16 is equal to negative 16. Because first you find the absolute value of 16, which is 16, and then make it negative because of the negative sign outside. Also, whenever you can combine terms within absolute value bars, do so before finding the absolute value. For example, to find the absolute value of negative 8 plus 2, you combine the negative 8 and the plus 2, which gives you the absolute value of negative 6, which is equal to 6. What's the absolute value of negative 87? 87. What does this expression equal? Negative 80. What does this expression equal? 5. You know, most people these days are familiar with this little device. With it, I can tell if my blood pressure is within normal limits. Great, because I don't have to give up potato chips yet. The normal healthy level for maximum blood pressure, called systolic pressure, is about 127 for men my age. If my pressure was a lot higher or lower than that, I might have a problem. Doctors have created a special index that shows how far a person's blood pressure is from normal. Because deviations on both sides of normal are important, they use absolute value to produce an index that consists only of positive numbers. The formula they use is P sub D is equal to the absolute value of P minus P bar, where P is a person's systolic blood pressure and P bar is the normal pressure of 127. P sub D stands for pressure difference from normal. The index you get from using this formula starts at 0, which represents a patient whose blood pressure exactly matches the norm, and goes up from there. To see how this works, let's find P sub D for the blood pressures of the following group of people. The first patient's blood pressure is 73, so putting that into our formula gives us P sub D equals the absolute value of 73 minus 127. That equals the absolute value of negative 54, which is 54. The second patient's pressure is 148. Using the formula gives us the absolute value of 148 minus 127, or 21. Now, how about that third patient? Whoa, this guy's in serious trouble. His blood pressure is 0. With our formula, his index number then is the absolute value of 0 minus 127, which is 127. An index scored that high means the person's already dead. Let's hope it was a typo. With a pressure of 66, the index value for the next patient is 61. And with a pressure of 188, the fifth patient's index value is also 61. One patient's pressure is too low, the other too high, but they're equally dangerous. With a pressure of 127, the last patient's index value is 0, meaning this patient's pressure is exactly normal. Converting blood pressure readings into index values such as these is useful. They can be added to index values for other health indicators, such as the level of oxygen in the blood, to give a single number that sums up a person's health. Now, before we go farther with absolute value, let's define it a bit more precisely than we have up till now. The absolute value of any number A is A if A is greater than or equal to 0, and negative A if A is less than 0. The second part of the definition requires a bit of thought. It may look surprising because, as we've seen, the absolute value of a number is always positive. Well, that's in fact what the second part of the definition says. It just says it in mathematical terms. If A is negative 5, for instance, then the definition says that the absolute value of negative 5 equals negative 5, which is 5. The definition of absolute value comes in handy when we have variables within the absolute value bars. For instance, how would we find the absolute value of the expression m minus 2 if we know that the value of the variable m is less than 2? Well, if m is less than 2, then the quantity inside the absolute value bars has to be less than 0, because 2 minus 2 is 0. So using the second part of our definition, we can write the absolute value of m minus 2 equals negative the quantity m minus 2. This equals negative m plus 2, or 2 minus m. As with many of the other algebraic skills we've learned, our knowledge of absolute value is most useful when applied to the solution of equations. Let's start small. The absolute value of x equals 3 can be solved by finding all the numbers that are 3 units from 0. Well, there are two values that satisfy this condition, 3 and negative 3. So the solution to the equation, the absolute value of x equals 3, is the set 3, negative 3. This example illustrates two rules that will help us solve more complex equations involving absolute value. The absolute value of any number a equals another number b if and only if A equals B or A equals negative B. Likewise, the absolute value of A equals the absolute value of B if and only if A equals B or A equals negative B. Let's see how to use these rules to solve the absolute value equation, the absolute value of 8 minus 3m equals 14. Using the first property, we know that either 8 minus 3m equals 14 or 8 minus 3m equals negative 14. Now we can solve each of these equations. The solution set is thus the set -2, 22/3. The method we just learned to solve absolute value equations can be generalized to solve inequalities with absolute value. Consider the inequality, the absolute value of x is less than 5. Since absolute value gives the distance between a number and 0, this inequality is satisfied by all numbers whose distance from 0 is less than 5. On the number line, you can see that this includes all the numbers from -5 to +5. Now, we can write this as x is greater than -5 and less than +5. In a similar way, the solution of the absolute value of x is greater than 5 is going to be all the numbers that are less than -5 or greater than 5. And we can write that x less than -5 or x greater than 5. These two examples illustrate the two basic rules used to solve absolute value inequalities. They're similar to the rules we just learned for equations. The absolute value of A is less than B if and only if A is greater than -B and less than B. The absolute value of A is greater than B if and only if A is less than -B or A is greater than B. We can use these properties to solve inequalities like this one. By the first rule, we know that the absolute value of x minus 2 is less than 5 if and only if x minus 2 is greater than -5 and less than 5. We can simplify this inequality by adding 2 to each portion, producing x is greater than -3 and less than 7. Thus, the solution is the interval between -3 and 7. You can see that working with absolute value is really just a slight twist on what we already know. We can apply all our skills of factoring, combining terms, solving equations, and solving inequalities to the solution of absolute value problems. We've now completed the first phase of this course in college algebra. We've come quite a long way in our ability to solve problems. We've learned to represent unknown quantities with variables and have discovered many ways to work with such variables to solve problems that would otherwise be unsolvable. We're going to summarize and review these skills by looking at fireworks, gliding, and potato chips. As different as these situations are, they will all exercise our ability to identify variables, set up algebraic expressions, and solve equations and inequalities using the techniques we've learned thus far. A modern fireworks display is a marriage of art and science. The art lies in the timing of the various kinds of shells and in the arrangement of color and sound in the night sky. The science lies in the creation of the fireworks themselves, which can be remarkably complicated and difficult to make. Yet despite constant improvements over the years, the main explosive ingredient of all fireworks, a substance called black powder, remains essentially unchanged from the powder invented by the Chinese more than 1,000 years ago. Black powder is a blend of 3 simple ingredients: potassium nitrate, also known as saltpeter, charcoal, and sulfur. When combined in the ratio of 75 parts saltpeter, 15 parts charcoal, and 10 parts sulfur, these ingredients make a powerful explosive. This basic 75-15-10 ratio creates black powder that burns very hot and fast. Fireworks makers often alter the basic ratio in order to slow down the reaction, producing a cooler and thus redder explosion. The ingredient they vary most often is sulfur. Suppose, for instance, that we have a standard 30-pound shell filled with black powder at the standard 75-15-10 ratio. Let's say I wanted to create a cooler burning shell by increasing the sulfur content to 12 parts. That would make the explosion redder. Now, I could just add some pure sulfur to do that, but because trajectory calculations are based on a 30-pound shell, I don't want the total weight of the shell to change. That means I have to remove some of the black powder from the shell first and then replace it with sulfur. The question is, how much black powder must be removed from the shell and replaced with pure sulfur to bring the sulfur proportion up from 10 parts to 12 without changing the weight of the shell? Like most real-life problems, this one takes a little thought before we plunge in and start calculating. Let's start by identifying what we know for sure and what we need to find out by using algebra. Well, we know that the shell now contains 30 pounds of mixed black powder, and that the ratio of the ingredients in that powder is 75 to 15 to 10. By the way, since these proportions add up to 100, we can read them as percents. In other words, the black powder contains 75% saltpeter, 15% charcoal, and 10% sulfur. So, knowing that, we can figure out how much of each ingredient is present in the existing shell by weight. For instance, let's find out how much saltpeter is in the 30-pound shell. Since we know that 75% of the shell's weight is saltpeter, we can just multiply the total weight, 30 pounds, by 0.75 to get the weight of saltpeter in the shell. It's 22.5 pounds. Doing the same kind of calculations for the other two ingredients gives us the following weights. Now we know the weights of each ingredient in the black powder. This is a start towards solving the original problem, which was how much mixed black powder must be removed and replaced with pure sulfur to bring the percentage of sulfur up to 12% without changing the weight of the shell. Now let's look at what we don't know. Since we don't know how much black powder should be removed and replaced with sulfur, let's call that value X. Notice that X here stands for both the amount of mixed black powder removed and the amount of pure sulfur to replace it. Now we have the pieces of the problem. The next step is to determine the relationship between those parts and express them algebraically. We know the original amount of sulfur in the mixture. It's 10% or 3 pounds. We want to boost that percentage to 12. But to do that, we're going to have to remove some of the mixed black powder. And that means we're going to remove some sulfur as well. How much? Well, remember that we call the unknown amount of removed black powder X. So the amount of sulfur in that removed amount will be 0.1 times X, since the proportion of sulfur in the removed amount is the same as the proportion for the shell as a whole. Then we're going to add our unknown amount of pure sulfur, which is just X. And since we want the new amount of sulfur in the shell to equal 12% of the total 30-pound weight, we can set this expression equal to 0.12 times 30. Now we can use the rules of algebra to solve our equation. First, we can multiply to remove the parentheses. Now, combine like terms. Get the variable on one side, multiply by 10 to get rid of the decimals, and finally, divide both sides by 9 and simplify the resulting fraction. We've found our answer. If we remove 2/3 of a pound of black powder and replace it with 2/3 of a pound of pure sulfur, we'll increase the percentage of sulfur in the shell to 12% without changing its overall weight. Of course, the proportions of saltpeter and charcoal would be slightly changed by this substitution, but that change isn't enough to affect the performance of the display. Now let's take a look at an even loftier problem. When men first took to the air, they used gliders, simple wings of canvas and wood, to let them skim briefly down hillsides. Gliders were perfected by the Wright brothers, but then they attached a motor to one. Gliders quickly went the way of the horse and buggy. But with the advent of modern materials and advanced aeronautic design, gliders have made a comeback. Once towed aloft by a motorized plane, today's gliders can stay aloft for hours. Using only the wind and rising air currents called thermals, glider pilots can cover hundreds of miles in fast, silent flight. Successful soaring requires an intimate knowledge of aeronautics, weather, and math. Calculations must constantly be made to estimate things like distance achievable from a given height or the proper rate of descent to reach a destination. An essential piece of information in many of these calculations is the glider's height above the ground. This data is usually read off an instrument called an altimeter. But as with any equipment, altimeters sometimes don't work. When that happens, glider pilots can use algebra to calculate their height. If pilots can see a recognizable landmark on the horizon and they know how far away it is, they can use this formula to determine their height. D stands for the distance from the plane to the horizon in miles, and H stands for the height of the plane above the Earth in miles. Suppose that the altimeter in a glider went on the fritz, but that the pilot could see a landmark on the horizon 50 miles away. How high is the pilot? Since we know D is 50, we can substitute this value into the equation and solve for H. Since we have a radical on the right, let's square both sides to remove it. Now let's simplify the right-hand expression. Since there's no obvious way to factor this expression, let's complete the square to solve it. First, let's rearrange the equation. Dividing the coefficient 8,000 by 2 gives us 4,000, and squaring that gives us 16 million. Adding this to both sides allows us to factor and then apply the square root property. Working out both answers leaves us with either 0.3 or negative 8,000.3. Remember that our answer is in miles above the ground. That means that in this case, only the positive answer has meaning. We assume our pilot isn't 8,000 miles underground. We can disregard that answer and use the second answer, 0.3 or 3/10 of a mile, which is about 1,600 feet. We found that if a pilot can see a landmark 50 miles away on the horizon, he's flying about 1,600 feet above the ground. In actual practice, the formula we just used would probably be programmed into a calculator so that a pilot could just punch in his distance and determine his altitude. Now, what about those potato chips? At Frito-Lay, the potato chip business is big business. Every day, these workers box about $2.5 million worth of chips. Truckloads of raw spuds are transformed into an avalanche of finished chips. Like any company, Frito-Lay strives to keep quality high. Everything from the thickness of the sliced potatoes to the amount of salt sprinkled on the finished chips is constantly monitored. Algebra is a key tool in the quality control process. One measure of quality is the number of scorched, broken, or otherwise unsatisfactory chips in each bag. Frito-Lay wants to keep the number of bad chips per bag as low as possible. Since they can't check every bag, workers scoop samples from the production line every 30 minutes. But the inspection process is not as straightforward as just counting bad chips in a sample and stopping the line if the threshold is reached. The reason is that even with perfectly adjusted machines, bags will occasionally appear that exceed the allowable limit of bad chips. That's just natural variation at work. If the company stopped the line every time a non-conforming bag appeared, it wouldn't be in business very long. To avoid that problem, the inspectors average the results of 6 bags of chips taken over a 3-hour period. This way, the natural variation between bags is smoothed out and a clear picture of the production process is achieved. But using an average raises a problem. Suppose the company sets 18 as its maximum allowable number of bad chips in a sample. What average number of irregularities should they look for to be sure the line is working correctly? An algebraic formula is used to calculate this average. C is the process average, and L is the processing limit. That's the threshold that Frito-Lay sets as unacceptable. In this case, as we saw, the processing limit is 18 bad chips in a bag. Although it doesn't look like it at the moment, this is a quadratic inequality. And as we learned before, the way to solve the inequality is to treat it as an equality. Now, let's subtract 18 from both sides and subtract 3 times the square root of c from both sides. Now, if we square both sides and simplify, we get something that looks familiar, a quadratic equation in standard form. Now we can solve this equation to find out what average the Frito-Lay inspector should look for on a regular basis. Since the equation doesn't factor in any obvious way, let's complete the square. In this case, we have 2 positive answers, 9 and 36. Since we've set the limit of acceptability at 18 irregular chips per bag, clearly we can't look for an average of 36 irregular chips. 36 just doesn't make any sense in the context of our problem. So we can use 9 as the critical point in our inequality. If the Frito-Lay inspectors see an average of less than or equal to 9 irregular chips in each sample of 6 bags, they know that their process is under control and that less than 1% of bags leaving the plant will exceed the limit of 18 irregular chips. Who would have thought that so much math went into something as simple as a potato chip? In this program, we learned about the concept of absolute value, and we saw that we can solve absolute value equations and inequalities using many of the skills we already know. We also got a chance to look over our shoulder at how far we've come in our exploration of algebra, and we've come a long way. In the next program, we'll enter some new territory. We'll learn how to graph equations. We'll see that turning equations into pictures on graph paper is a good way to get a fast feel for many situations, such as the rate of potato chip production over time, or even the rate of potato chip consumption over time.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.